Welcome to 9.4. We'll be starting our study on vectors. Some of our objectives are to graph vectors, find a position vector, add and subtract vectors algebraically, find a scalar multiple and the magnitude of a vector, find a unit vector, find a vector from its direction and magnitude, and model with vectors. So we're talking about vectors a lot, and a vector is basically this line segment, but it tells us the direction we're moving in and how far. So just like in GRU, when we see vector and he's talking about vectors have direction and magnitude, that was exactly right. We're seeing which direction it's going in and how far it's going in that direction. So that's what vectors are talking about. For our first example, we will find the position vector v with initial point P and terminal point Q, and it tells us where these points are at 4, 9 and 4, 6. So if we look over here at this vector AB, we can see our initial point here at A and our terminal point here at B. That's what we're looking at in terms of P and Q. So this might look like something 4, 9. So if this was 4, and if these go by 4s, then we've got 4 and 9 about here. That would be our P, and our Q is 4, 6. So our vector is right here. And we can visually see what's happening to it, the direction it's going in, and how far. So let's find the position vector. Let's find out what the components of that PQ vector are. And in order to do that, we will use our formula V equals, and we're going to be taking x2 minus x1 and also y2 minus y1. And this is going to be 4 minus 4 and 6 minus 9 based off of the coordinates that P and Q are at. 4 minus 4 gives us a 0, and 6 minus 9 gives us a -3. So our vector V is -3j. And that makes sense because we're looking at it and it's just moving straight down. It's not moving side to side. So we wouldn't have any change in our I values, only our j values. So awesome. For example 2, find 3v minus 2w if v is 3i minus 7j and w is -5i plus 7j. So each of these v and w are representing a different vector. Just like over here on the side, we can see a and b are different vectors. V and w are represented by different vectors. And we can add or subtract these vectors together, and what happens is we just take our A and we put it, the end of it, we put B, and by putting them from head to tail, we can get A plus B, which would give us this new vector here, which is our components that we would end with. We could also subtract them. Here is an example right below the addition example where we can see here's our A vector, here's our B vector. But if we wanted A minus B, we would just take the negative of our B. So we would go this way, and this is our vector that represents going from A and minus b from head to tail. So to find these sums and differences of our vectors, what we're really doing is just putting them end to end and seeing what's the vector that gets us there. This vector is the one that took us from the starting place to the ending place after we put them head to tail. This is the vector that got us from our starting place to our ending place if we put them head to tail. Whether we're adding or subtracting, we're just finding this third vector that gets us from the starting place to the ending place. And that's what we're doing when we add and subtract. So if we take 3v minus 2w, let's look at some of the algebraic ways we can find this. Well, we know what v is, so 3, and we plug in v, that would be 3i minus 7j, minus 2, and w is negative 5i plus 7j. Now I'm just going to distribute, so 3 times 3 is 9i, 3 times 7 is going to be negative 21j, negative 2 and negative 5 is plus 10i, negative 2 and positive 7 is negative 14j. Now we combine like terms, so we're going to combine our i's and then combine our j's. For our I, we have 9 plus 10, so 19i. For our j, we have negative 21 and negative 14, so that gives us negative 35j. So this is the vector we would get by taking 3v minus 2w. We end up with a vector 19i minus 35j. Okay, next we're going to talk about magnitude. The magnitude is one of the components that vectors tell us. So one of the components is direction and the other is magnitude. Magnitude is its length, so how long is it going in that direction? That's represented by our magnitude. So we'll find our magnitude. It's represented by the double lines here. Find the magnitude of v if v equals negative 7i minus 7j. Our magnitude formula tells us to take negative 7 squared plus negative 6 squared and find the square root of it, because we're finding that distance. We're finding the distance from the beginning to the end of our vector, so it would make sense to be using our distance formula that we learned way back in geometry. So we have 49 plus 36. Finding the square root of this would give us the square root of 85. And we're going to leave it as the square root of 85. That's going to be the most accurate solution there. And that's our magnitude. That's the length of this vector v. Next, we'll talk about unit vectors. So the vectors are just one segment on this continuous line here. So what we're looking at is when we talk about a unit vector, we're not looking at the length of the whole vector. We want to know, okay, if I'm looking at the same direction, what would my unit vector be if I only wanted one unit in that direction? So we're looking at the same direction as this vector v, which is 7i minus 4j, but we're only going to find the unit vector, so one unit in that direction. What would the vector be? What would the components be, the I and j, showing us just one unit moving in that direction. So our unit vector formula is going to be u is our vector over the magnitude of the vector. So if we find the vector and we divide it by its magnitude, that'll give us the one unit in that same direction. In this case, our vector is 7i minus 4j, and our magnitude is going to be 7 squared plus negative 4 squared and the square root of this. So we're going to have this, I'm just going to solve the bottom part first. So I have 49 plus 16, and we're going to take the square root of it. And that gives us the square root of 65. And we could stop here, but we're not going to. We're going to rationalize that denominator, so I'm going to get that root out of the bottom. So when we multiply these out, we're now going to have our root 65 on the top and no roots on the bottom. So on the top, now we have 7 root 65, and on the bottom, we just have 65. This is for our I value, and then minus 4 root 65 over a 65 for our j value. So our unit vector in this direction of v is 7 root 65 over 65i minus 4 root 65 over 65j. This is just one unit in the same direction that v is going. Next, let's find the vector v whose magnitude is 7 and whose component in the I direction is both positive and equal to the component in the j direction. So this is almost like a vector riddle. They're giving us different clues about our vector, and we're supposed to piece together what we know about vectors and how they work in order to find out what the vector is. So I'm going to start with our v equals magnitude of v times my cosine of alpha I plus sine of alpha j. So we'll start with that formula and plug in some of the things that we know. What we know is that our magnitude is 7 and our I is positive and equal to j. So if our magnitude is 7, that means that this piece is 7. So I have v equals 7, cosine of some angle in the I component, sine of some angle in the j component. So now we're just missing our alpha. What is this component, this angle in I and j? And it tells us that I is positive and equal to j. So I and j are both equal, and I has to be positive. So now we're thinking, what value is cosine and sine? What angle are cosine and sine values the same? And this should be a pretty quick one for you now that we've done our trig functions in unit circle for so long that we should know at 45 degrees, our sine and cosine are both root 2 over 2. So that's where our sine and cosine have the same value at one angle. So my alpha here is 45 degrees. So I have 7, and then we have cosine 45 degrees in the I direction, sine 45 degrees in the j direction. And so, since cosine of 45 and sine of 45 are root 2 over 2, we can further simplify this into 7 root 2 over 2i plus 7 root 2 over 2j. And that's our vector. We've found the answer to the riddle. Okay, find the vector v given that the magnitude is 9 and the angle it makes with the positive x-axis is alpha equals 225 degrees. So again, it's very similar. It's almost like a riddle that we're trying to figure out what this vector is when they give us some clues. Again, let's start with our same formula that we did before. V equals the magnitude of v times cosine of some alpha I plus sine of that alpha in the j. Now, again, they've given us the magnitude is 9. The angle is 225 degrees. Also, it's positive with the x-axis, so that is moving it in the way that we're used to. It's moving 225 degrees from the x. So in a way that we move, it's almost like our default. It's not moving in the negative direction. All right, our magnitude is 9, and our angle, or our alpha, is 225 degrees. So we'll plug everything in that we know. Now, what is the cosine at 225 degrees? Well, that's negative root 2 over 2. And then what is sine at 225 degrees? That's also negative root 2 over 2. So now we've got everything is filled in. We've even simplified our sine and our cosine. Let's distribute that 9 in and have our vector. V equals a negative 9 root 2 over 2 I minus 9 root 2 over 2 j. And that's our vector V. Okay. Our final example for this section is an application problem. A small plane is flying at a speed of 200 miles per hour on a bearing of north 55 degrees east. The wind is blowing from west to east at 35 miles per hour. Approximate the ground speed of the plane to the nearest mile per hour. Approximate the true course of the plane to the nearest tenth of a degree. So, some of the things we want to find is the ground speed of the plane and the true course of the plane. Those are the two things we're looking for, two answers. Some of the information we have. The plane flies 200 miles per hour on this bearing. The wind is blowing from west to east 35 miles per hour. Those are important for us. So, I like to understand what it is that we are looking at. So visually, if I have a compass, this is north, and this is east. North 55 degrees east, so that's 55 degrees east from north. So from north, we're 55 degrees going that way, which means if we are looking at it the way that we've been doing our vectors, we have a 35-degree angle. That helps us out a little. It helps me out anyway to understand what I'm looking at here. So the first thing that I'm going to do is I would like to get a vector of the plane. So a small plane is flying 200 miles an hour on a bearing of north 55 degrees east. So what's our plane in the air? We'll put V sub A to represent the vector of the plane in the air. That would be represented by, here's first our magnitude, so 200, and then we have cosine. We have our theta is that 35, and that's our I. Our sine of 35 is our j. So this will simplify to, if I put cosine 35 degrees through my calculator, multiply it by that 200, and then I do the same with sine of 35 degrees, multiply that times the 200, this is going to give us about 163.83 I plus 114.72 J. So this is our vector of the plane in the air. And another important vector we want is the vector of the wind. So the wind is going from west to east at 35 miles per hour. So that's just 35 in the I component and nothing else. It's moving in the positive direction, a magnitude of 35. So that's it. It's not going up or down. It's just moving in the east direction. Now, in order to find the ground speed of our plane, let's see, we'll do that in this. For the ground speed of our plane, we are going to take the air speed of our plane and add the wind, and that'll give us the ground speed. So this gives us VA, the vector of our plane in the air, was 163.83 I plus 114.72 J, and then we're adding the wind, which was 35 I. Now we just combine our i's because the J doesn't have anything being added to it. So 163 plus 35 gives us 198.83 I plus 114.72 J. So this is the vector of our ground speed of the plane. So this is the vector of the plane if it were moving on the ground. So this is the air plus the wind. We want to know its ground speed, so from beginning to end, that would be our magnitude. So we're going to take the magnitude of that vector because that's going to give us its speed from beginning to end. How fast is it going, right? So we have 198.83 squared plus 114.72 squared. Make the square root of all of this. This gives us about 229.55, but it wants it to the nearest mile per hour. So the nearest mile per hour is going to give us 230 miles per hour. So that's the approximate ground speed of the plane. Now let's find the approximate true course of the plane. So with the wind acting on the plane, is it actually moving at this 35-degree angle, or what is the wind affecting the angle? So what we'll do in order to find our angle is we'll take tangent of alpha, and remember tangent is y over x, so we have our 114.72, and we're putting that over the 198.83. And if we want to find alpha, that means we have to take the tangent inverse of everything. So alpha is approximately tangent inverse of this, 114 over 198. This gives us about 29.9, and that one also wants the nearest tenth of a degree. Okay, nearest tenth of a degree gives us a 29.9. So yeah, we can leave it there. You can also say, okay, it's about 30 degrees. Since we put the other answer in a whole number, we can round this one to a whole number as well. Either one So we've found the 30 degrees. This actually, I'm not going to box it. This one is not our answer just yet, because if we're looking at our compass, we found that it's at a 30-degree angle. But what is that in terms of a plane's bearing? Well, that's going to be north. What from north? Well, in order to complete this 90-degree angle, we're missing 60. So it's north 60 degrees east. So from north, we're heading 60 degrees east from north. So our plane is traveling north 60 degrees east. And that's what we would put as our final answer. We wouldn't end with the 30 degrees because that wouldn't give us the right bearing. And that is our introduction to vectors.